So in this PenCast, we're going to take a look at the Clausius Clapeyron equation, which is used to look at the relationship of vapor pressure and temperature for a liquid. It's also used to calculate the heat of vaporization, the molar heat of vaporization, delta H vap for a solution, for a liquid rather. The equation, let's back up. If you recall from our notes, we saw that a graph of vapor pressure, P vap, versus temperature has the form of an exponential function. Okay? So because it's an exponential function, we're not surprised then to see that there's a logarithmic relationship between vapor pressure and temperature, since the logarithmic function is the inverse of the exponential function. The typical way that the relationship is written says that the natural logarithm, ln, of the vapor pressure, P vap, is equal to negative delta H vap over R times the reciprocal of temperature, 1 over T, plus C, a constant. So this is the Clausius Clapeyron equation. In it, P vap is your vapor pressure of a liquid. Delta H vap is your molar enthalpy, also called heat of vaporization. R is the ideal gas constant, 8.314. We're using the ideal gas constant of 8.314 so that our units will be SI. When we use SI units, the delta H vap will be in joules per mole. Okay? Heat is a form of energy, so joules per mole. Temperature in the Clausius Clapeyron equation is temperature in Kelvin, and the C at the end is simply a constant which we're not really interested in. When you look at the Clausius Clapeyron equation, as ugly as it may seem, as complicated as it may seem, it actually has an interesting underlying structure. You can overlay the equation of a straight line, which tells you that if instead of graphing vapor pressure versus temperature, you were to graph the natural log of vapor pressure versus the reciprocal of the Kelvin temperature, so K to the minus 1, the resulting graph should be a falling straight line. Falling because the negative sign in the equation means that the slope will be negative. So the slope of the line is negative delta H vap over R. So if you wanted to calculate delta H vap, you would simply multiply your slope by negative R to get the delta H vap in joules per mole. Okay, joules per mole. Let's take a look at an example, and you're going to need your graphing calculator to do this. So pause and get your calculator out if you don't have it. I'm going to give you the vapor pressures of 2-propanol at several different temperatures. So P vap and temperature. Okay. The temperatures we'll look at, I'll give you the Kelvin temperatures. So we'll say 300 Kelvin. The vapor pressure is 6.59, we'll say 6.6 kilopascals. That was 300 Kelvin. At 311 Kelvin, I'm taking these values, by the way, from our website. 311 Kelvin, the vapor pressure is now 12.7 kilopascals. We'll jump up to 321 Kelvin, and the vapor pressure is now 21.8. We'll go up to 332 Kelvin, and the vapor pressure is now 36.5. We'll do a couple more. 342 Kelvin has a vapor pressure of 56.9 kilopascals. And finally, we'll stop at 351 Kelvin. The vapor pressure is 86.8 kilopascals. Now, if you have your graphing calculator in front of you, turn it on and go to your Stat menu. Press the Edit button, and that should bring up your lists. Go up, put your cursor on top of the L1 symbol and clear Enter to remove any data. Do the same thing for the remaining lists. Go to L2, put your cursor on the L2 and press clear Enter, and do the same thing for list 3, list 4. In list 1, let's enter the temperatures. So 300 Kelvin, 311 Kelvin, 321 Kelvin, 332, 342, and 351. In your list 2, enter the vapor pressures. 6.6, 12.7, 21.8, 36.5, 56.9, and 86.8. Double check that you've got the same number of values in each list. And now let's go make a stat plot. So second function above the y equals button, it says stat plot. Plot number 1, turn it on if it's not already on. You want the first type of graph, a scatter plot. Our X list will be list 1, L1, that's our temperatures, and our Y list will be L2, our vapor pressures. Okay? If I'm going a bit fast for you, pause and get to this point. Alright, now you want to press zoom number 9, zoom stat, to make the graph visible, and sketch for yourself the graph that you see. So PVAP and temperature. Now I'm going to do a scale for the vapor pressure that starts at about 0, and I'm going to go up to about 110. You'll see why in a minute, and that's kilopascals. Temperature in Kelvin will go from 300 up to, we'll say 300 and, why don't we go up by tens roughly, 310, 320, 330, 340, 350, 360, 370, something like that, 370 Kelvin. Now, do your best to plot these points as you see it on your graph, on your calculator. You're not going to be perfect, but estimate 300, 311, okay, 321, okay, I'm going to just start estimating. Okay, that's basically what my graph looks like. Okay? Now, one thing I want you to note. If you find the vapor pressure of 101.3 kilopascals, and just sort of label it, this is 101.3 kilopascals, and draw a dotted line over to your graph, and go down to the x-axis. Now I haven't sketched my graph very accurately, but this temperature that we see down here would be referred to as your normal boiling point. Okay? The definition of boiling point, of normal boiling point, you can write the definition down for yourself. It's the temperature at which the vapor pressure of a liquid is standard pressure, or 101.3 kilopascals. So the normal boiling point, one more time, is the temperature at which the vapor pressure of a liquid is equal to 101.3 kilopascals. So that's the normal boiling point of a liquid. More generally speaking, you can write down a second definition. The boiling point of a liquid, okay, notice I'm taking out the word normal now. The boiling point of a liquid is the temperature at which its vapor pressure is equal to the outside surrounding air pressure. So the boiling point of a liquid is the temperature at which the liquid's vapor pressure is equal to the outside surrounding air pressure. Notice that the second definition is more flexible in that if the outside pressure were to change, then the boiling point of the liquid would change. Because of that, when water is at sea level, it boils at 100 degrees Celsius, but when water's up at, say, Denver, Colorado, and you're on the top of a mountain, the boiling point is much lower because the the air pressure higher up on a mountain is less than the air pressure down here at sea level. All right, let's make a second graph. Okay, we're going to test the Clausius Clapeyron equation now. On our second graph, we want to graph the natural logarithm of vapor pressure versus the reciprocal of the Kelvin temperatures. So go back to your stat menu on your calculator, number 1, edit, and move over to list 3. List 3 will make it as the reciprocal of our temperatures. So if you put your cursor up onto the L3 symbol, at the bottom of your screen underneath the list, it should say L3 equals. I'm going to let it say that L3 equals, now you could type in 1 divided by L1, or what I'm going to do instead is say second function L1. L1 is right above the number 1 on your keypad, and there's a button right below the math button on your calculator that says x to the minus 1, and I'm going to press that. So my calculator says that L3 equals L1 to the power of negative 1, which of course means the reciprocal of L1. So I'm taking the reciprocal of the temperatures that are in list 1. Press enter, and you see a bunch of small numbers, which makes sense. Since the temperatures were large, the reciprocals are small. Now move over to list 4. And in list 4, we want to take the natural logarithm of the vapor pressures. The vapor pressures are in list 2, so with your cursor up on top of the L4 symbol, at the bottom of your screen it should say L4 equals. We'll press the LN button, which is right underneath the log button. So this is the natural log button. And we'll say take the natural log, a bracket is open there, and it will take the natural log of list 2, so second function L2. And press enter, and you should get values that go from 1.89 up to 4.46. Now you can indicate that on our graph. The smallest value for the reciprocal of temperature would be about 0.00285, and the largest value is about 0.00333. Meanwhile, the smallest value for the natural log of vapor pressure is about 1.887, and the biggest value is about 4.464. Now we'll go back to the stat plot, second function stat plot, right above your y equals button. We can go in and turn plot number 1 off, and now go up to plot number 2. turn plot number 2 on. Okay, this way we can go back if we want to the graph that we made earlier. We're making a second graph in plot number 2. So with plot number 2 turned on, we still want the first type of graph, a scatter plot. Our x list is now list 3, so second function L3, that's the reciprocal of temperature. And our y list is second function L4. That'll be the vapor pressure's natural log. Again, press zoom, and then number 9, zoom stat, and what you should see on your calculator is a straight line of data falling down like that. And what we want now is to find the equation of the line of best fit. So I'll go second function quit to get back to my main screen. Now I'll press Stat. I'll go to the right to the Calc menu. Option number 4 is linear regression, AX plus B. So that's what I'll choose. And now you recall we need to tell it the X list, comma, Y list, and then we'll also tell it to graph the equation for us as function Y1. So press second function L3, that was our X list of the linear graph, comma, the button right above the number 7 on your keypad, second function L4, comma, the VARS button, V-A-R-S, right beside the clear button. Go over to Y variables. Number 1 is functions, and we can choose number 1, Y1. So at this point, your screen should say linreg AX plus B, L3, comma, L4, comma, Y1. Press enter. The slope is something we're going to want, so let's indicate that on our graph. The slope is negative 5267, which is equal to negative delta H vap over R. If you press graph, you should now see a straight line falling through our data. Alright, so let's use the slope to calculate delta H vap for our 2-propanol. So we can say here that delta H vap, the heat of vaporization, is equal to the slope, negative 5267, times R, which is 8.314. Now, I'm leaving the units out here, but if you recall that when you put SI units into a formula, you get SI units out. If you want, I can show you how the formula units work, but basically I'm going to multiply negative 5267. I just realized I forgot a negative sign in R. We're supposed to multiply the slope by negative R. Okay? If you look back at the Clausius Clapeyron equation, your slope is negative delta H over R. Therefore, delta H is the slope times negative R. This way our answer will become positive. So times negative 8.314, and we get an answer of 43,000, and I'm going to round this off, 800 joules per mole, which, if we want, we could express as 43.8 kilojoules per mole. Okay? There's our value for delta H vaporization. So that's one way to use the Clausius Clapeyron equation. And it's used for graphing when you have lots of data like that. And then the slope of the graph ends up giving you your delta H vap. There's another way to use the Clausius Clapeyron equation, though, and that's when you don't have a whole set of data, but when you have 2 points. So 2 sets of data, 2 values, pressure at one temperature and a pressure at another temperature. For example, let's use the data that we had in our table and the delta H vap that we have here to calculate the normal boiling point of 2-propanol. Okay? To do this question, we need to derive a related form of Clausius Clapeyron. So let me just say here that the natural log of P1 of one vapor pressure is equal to negative delta H vap over R times 1 over T1 plus C. So I've used the Clausius Clapeyron at one pressure and one temperature, a P1 and a T1. Let's do the same thing. The natural log of P2, a new pressure, equals negative delta H vap over R times 1 over T2 plus C. Okay? Now we're going to play a little trick. We're going to subtract those two equations. The natural log of P1 minus the natural log of P2 is equal to negative delta H vap over R times 1 over T1. And I'm going to write minus negative delta H vap over R times 1 over T2. Now on the left, we can apply a log rule. Okay, if you look back in your notes, look at the 3 rules for logarithms that we wrote down, and I believe it was the second rule that said the logarithm of a quotient is equal to the difference of 2 logarithms. If we apply that rule backwards here, we have the difference of 2 logarithms. Therefore, that should equal the natural log of P1 divided by P2. That'll equal, on the right side, we notice in these two terms that they both have this negative delta H vap over R. So I'm going to factor that out front, negative delta H vap over R times 1 over T1 minus 1 over T2. All right, now some authors take the negative sign from the delta H vap and they move that negative sign into our brackets, which would then result in, instead of a 1 over T1 minus a 1 over T2, it will give you a 1 over T2 minus a 1 over T1. Okay, so if you see that, you'll notice that the delta H vap is positive in the equation and your temperatures are reversed. It's the same equation with the negative sign put into the brackets. I'm going to put a box around this equation, and I'm going to call this the 2-point Clausius Clapeyron equation. Okay, this is for when you have just 2 points, a P1 and a T1, a P2 and a T2. Okay, now going back to the data table that we had earlier, I'm going to let my P1 equal and my T1 equal. And I can pick any points from the data table. Why don't I pick the very first one? So 300 Kelvin was the T1, and the vapor pressure was 6.6 kilopascals. But the question we're trying to answer says to calculate the normal boiling point of 2-propanol. We recall the definition of normal boiling point. It's the temperature at which the vapor pressure is equal to standard pressure. So because of that, I'm going to let P2 equal standard pressure, which is 101.3 kilopascals. And the thing I'm going to solve for is T2, because the temperature at which the vapor pressure equals 101.3, this temperature is my normal boiling point. Okay? The last thing that we need is our delta H vap, which we had above, and I want to remember to use the SI version, 43,800 joules per mole. Okay? Make a note for yourself, you need to use here the SI version, joules per mole, not the kilojoules per mole that we derived. A question could have easily given you the delta H in kilojoules per mole. You would need to then convert to joules per mole. So let's take what we know and put it into the equation for the 2-point Clausius Clapeyron. The natural log of 6.6 over 101.3, P1 over P2, is equal to negative 43,800 over 8.314 times Now look at how I'm going to write this. Instead of a 1 over T1 minus a 1 over T2, I'm going to write that as 300 to the minus 1, because I have that button on my calculator for x to the minus 1, minus T2 to the minus 1. And of course that means 1 over 300 and 1 over T2. Now I'm going to grab my calculator and I'm going to evaluate the left-hand side. The natural log of 6.6 divided by 101.3 is equal to negative 2.73, and that's equal to, I'll divide the two numbers out front, negative 43,800 divided by 8.314, negative 5268 times 300 to the minus 1 minus T2 to the minus 1. Now I'll divide negative 2.73 by negative 5268. I get an answer of positive 5.18 times 10 to the minus 4, which is equal to 300 to the minus 1 minus T2 to the minus 1. Now I'll throw my T2 to the minus 1 to the other side of the equation, where it becomes positive T2 to the minus 1 equals 300 to the minus 1. Take away the 5.18 times 10 to the minus 4. So I threw that to the other side as well. Now I grab my calculator, and I'm going to use that little x to the minus 1 button, which is right below the math button on your calculator. 300 to the minus 1 minus 5.18 times 10 to the minus 4. Be sure you're using your scientific notation button, the EE button, equals 0.00282.2815. Now I need to get T2. Since this was the reciprocal of T2, then T2 would equal the reciprocal of this tiny number. Okay? Equals 355 Kelvin. Okay? Now to put that into some terms that are more familiar to us, I'll just convert it back to the Celsius temperature, and it's 82 degrees Celsius. I don't know if you recall that from grade 9 science, where you did find the boiling point of 2-propanol, but this is the number that we listed back in grade 9. So this is the normal boiling point of 2-propanol. Okay? Another common question might ask you to find the vapor pressure. Find P-vap for a liquid. We'll still stay with 2-propanol at some temperature. If we look back at our data table, we went up to 351 Kelvin. Why don't we ask for vapor pressure at 361 Kelvin? Okay? Since our normal boiling point was 355 Kelvin, we're anticipating that this vapor pressure would have to be higher than the 101.3 kilopascals. So what we'll do here is we will set up our equation again, the natural log of P1 over P2. Sorry, let me back up. I'll list some variables here. So P1, it doesn't matter whether you use a value from the data table for P1 or if we let the unknown be P1. I'll let the unknown be P1. Therefore, my T1 is 361 Kelvin. I need a P2 and I need a T2. Well, why don't I use the normal boiling point? 101.3 kilopascals would be my P2, and 355 Kelvin was the normal boiling point. Now, you could easily switch these and let P1 be the 101.3 and T1 be the 355, then P2 would be the thing we're solving for, and T2 would be 361. Okay? It doesn't matter which you call which. And of course, we still need delta H vap. and we still need it as the 43,800 joules per mole. So we'll substitute everything into the 2-point Clausius Clapeyron equation. The natural log of P1 over 101.3 is negative 43,800 over R times T1 to the minus 1 minus T2 to the minus 1. Now everything on the right-hand side can just be evaluated. So negative 43,800 divided by R times, open a bracket, 361 to the minus 1 minus 355 to the minus 1, close your bracket, equals 0.247. And that's the natural log of P1 over 101.3. Now here, you don't want to commit a very silly mistake. Many students at this point want to multiply both sides by 101.3. Of course, you can't do that because the left-hand side does not just say the natural log of P1, then divided by 101.3. It actually says the natural log of P1 over 101.3. In other words, the 101.3 is within the natural logarithm, so you can't simply multiply by it. Similar to trigonometry, for example, a trigonometric function where a number was inside the sine, or the cosine, or the tangent. So what we need to do here is undo the natural logarithm. And to do that, we just need to switch back to exponential form. I'm going to just remind you in the margin. So for example, the natural log of, the base 10 log, one you're more familiar with, of 1,000 was equal to 3. This is true because 10, the base, to the power of 3 is 1,000. Okay? So if we use the same logic, we remember that the base of the natural logarithm is the number e. So I'm going to write e, the base, to the power of that number out to the right, to the power of 0.247, must equal the stuff that was inside my natural logarithm. So P1 over 101.3. Okay? On your calculator, you're just doing second function natural log. That brings up e to the power of 0.247. And then we get 1.28. Okay? And then finally, P1 is 1.28 times 101.3 equals 130 kilopascals. The vapor pressure at 100, temperature rather. Did I get that right? Yeah, the vapor pressure at 361 Kelvin. Sorry, it's late. Anyway, I hope that helps. This was an overview of the Clausius Clapeyron equation. Its original form, natural log of Pvap equals negative delta Hvap over R times 1 over T plus C. From that, we applied y equals mx plus b and saw how to make a linear graph. We saw how to take some data for two propanols, vapor pressures at different temperatures, and then we graphed it both as a straightforward vapor pressure curve, and we saw the exponential function, and then we graphed it according to the Clausius Clapeyron equation with the natural log of Pvap on the y-axis and 1 over t on the x-axis. The result was a falling straight line whose slope was negative 5,267. We then multiplied that by negative r to get delta Hvap. With this, we can now answer questions like finding the normal boiling point of 2-propanol, or finding a vapor pressure for 2-propanol at some temperature. To do that, we derived a 2-point version of Clausius Clapeyron so that we don't have to graph, we can simply do it algebraically. That 2-point version, natural log of P1 over P2 equals negative delta H over R times 1 over T1 minus 1 over T2. We saw two sample problems with that, and that basically covers the Clausius Clapeyron equation. You need to be able to do all of that for your test and for your exam. Good luck.